Last time we started section 6.1, the set of rational numbers, and we had taken a look a little bit at a little bit of vocabulary, a little bit of different pictures or imagery of how we can represent fractions. And today we're going to take a look starting with some historical perspective. Fractions have been around a really long time. So the Egyptians actually first used fractions, and theirs were very interesting. Their fractions all had numerators of 1. And so in order to write the number 7 over 12, they wouldn't have written it as 7 over 12. It would have been written something like 1/4 plus 1/3. The numerator has to be a number 1. So that's kind of a different way of thinking about it. The Greeks adopted fractions with denominators of 60 from the Babylonians. We still use this idea of base 60 when we talk about measurements of angles. And then the Hindu are the ones who developed our modern bar between the numerator and the denominator in Europe in around the 1500s. So fractions have been around for a really long time, this representation of a rational number. I mentioned a little bit about models last time. We're going to talk a little bit more about it today. There are 3 different types of models that can be used for fractions, at least 3 that we're going to discuss. The first one is an area model. It says use of a rectangle. It wouldn't have to be a rectangle. It could be another shape like a square or a circle or a triangle, but it's a solid shape, right? A connected, complete shape. And then you're shading a portion of it. And so we encountered this last time, both with circles and with rectangles. An example of this for, say, the number 3 over 4 might look something like this. And then it would be split into quarters, and you would see 3 of the 4 quarters shaded in. So this would be an example of an area model. One of the models that we didn't talk about last time actually was the second one. We didn't talk about number line models. If we use that same fraction 3 over 4, a number line model will have our number line. It will mark, that's probably not quite long enough, let me make it a little bit bigger. It will mark off the 0 and the value 1. And then we will split the pieces in between. So this would be into 2 pieces, this will be split into 4 separate pieces, and then our fraction 3 over 4 would be right here, and we'll just mark it with a dot. So this would be the number 3/4 from a number line model perspective. Now we saw the set model last time that looked like coins or discs. So if you were doing the number 3 out of 4, there's lots of ways that it could be drawn, but a very natural one would be to draw it with discs. So we'll draw this one, and then I'm just going to copy and paste it. So we would have 4 objects, and then we would shade in, whoops, my shade, it's too big. Shade in 3 of them. So that would be a representation in a set model of the number 3/4. And I mentioned last time that this model is really quite different because they're individual objects and you have a portion of them as opposed to one object and you have a portion of the one object with both of the other models actually. One of the things that you'll remember for sure about fractions, even if you don't remember the name, is called the fundamental law of fractions. So if we have the fraction a over b, and n is any non-zero integer, we can actually take a over b and multiply the numerator by n and the denominator by n, and it will create an equal fraction. It will have equal value. One of the places that we see this used a lot is in reducing fractions, right? Making them into their smallest form. Like this image over here that I did of 3/4, instead of having 4 objects and shading in 3 of them, I could have 8 objects and shade in 6 of them, and it would still be the same ratio as having the 3 to 4 objects shaded in this way. So this is one of those things that we tend to remember about fractions, the ability to multiply or to divide the numerator and denominator by the same value and it not change the value of the overall fraction. Now, simplest form is the result of simplifying or dividing the numerator and the denominator by whatever they can both be divided by. So a rational number a over b is considered to be in simplest form if the greatest common divisor of the numerator and the denominator is 1. In other words, you can't actually divide them out any further and make them smaller. So they have no common factors. So I'll just put an example in right here. If I had, I'll use 6 over 8 since I just mentioned it a moment ago, we would say 6 over 8 is not in simplest form because I have the ability to divide, and I'll make mention of this in a minute, but division is really the same as multiplication because instead of doing division, I could have thought of it as 6 over 8, what I have, as multiplication by the fraction 1/2, so it has that same form. So either division or multiplication. But 6 divided by 2 is 3, and 8 divided by 2 is 4, and then if at that point I consider the 3 and the 4, I can't do that process again. 3 and 4 don't have any numbers that they both in common divide by. So that would be reduced or simplified form. All right, so I have an example where we actually have a fraction, 7 over negative 14. It wants us to write 3 fractions equal to this one. So there's infinitely many options of things you could write. So write down for me 3 different fractions that you believe are equal to 7 over negative 14. And then we'll just chat real quick and make sure that everybody's on the same page on how to think about that. Somebody give me an example, just one of the numbers you wrote down. Negative 1/2. So I'm going to write it this way, negative 1 over 2. You could write the negative on the top, you could write the negative on the bottom, or the negative out in front. And it's actually true that if I write these different like this, that would be another example. So I actually have 2 examples using the same, numerator and denominator numerical value. I just changed the location of the negative. Somebody give me another example that you have. Okay, so negative 14 over 28. And of course I could put the negative on top and bottom. I won't do that on every fraction, but I could. What else do you have? Give me one more.
Negative 21 over 42.
Lovely. What about 3 over 6? I'll put a negative on the top. Is that true? Yeah, so there's a couple different ways to think about this. The first one that you guys gave me, the 1/2 one, is kind of thinking about dividing the top and the bottom by 7, right? Because they both have a 7 in common. The middle two, the 14 over 28 and the 21 over 42, you probably looked at the 7 over 14 and either multiplied by 2 on top and bottom or multiplied by 3 on top and bottom. Perfectly acceptable. What did I do to get negative 3 over 6? Because I'm sorry, but 7 over 14 doesn't sort of divide or multiply evenly, nicely, beautifully to get 3 over 6. But why does it work? Yeah, if I take the simplified 1 over 2, ignore the negative for just a moment, just the 1/2 part right there, and I actually manipulate with that one, it's still acceptable, right? Because these are all equal fractions that we've created. So once you've manipulated it into one form, you could use the manipulated form to get yet another option as well. So again, infinitely many options of things that we could write down as fractions equal to 7 over negative 14. Great. All right, this problem is kind of interesting. what you will see that I will do, and what you will see that section C will do a lot of times, is try to present problems where students would have common mistakes. There's a mistake that they would make for, I don't want to say a legit reason, but there's a reason that they make the mistake based on stuff we do in other contexts. For example, on this one, if I'm trying to reduce the 42 squared over 35 squared, it's very tempting to cancel out the squares. Okay? You don't have to tell me like I was going to do that, but probably some of you thought about that initially. You may have caught yourself and you may not have. But it's really tempting to cancel out the squares because we cancel things out, right? Like that's an operation that we do, but we can't cancel out squares. Let me actually show you a real simple one, and so you can see why that idea wouldn't work. And I'll just do 1 over 2. If I had 1 squared over 2 squared, and I were really able to do, this sort of canceling out of the squares business, I would get the fraction 1/2, right? But if I actually multiply them out, 1 squared's 1 and 2 squared's 4, clearly 1/4 and 1/2 are not equal. Okay? So we don't have an operation that allows us to cancel squareds. We do have operations that allow us to reduce fractions by using multiplication and division for our reducing process, right? So instead of trying to cancel out the squareds, it would be easier for us, I'm just going to rewrite it here, to take a look at how these numbers break down. So ignore the squares for a moment. Can you tell me 42? What are two numbers that multiply to give you 42? All right, 7 and 6 are really good ones. So 7 times 6, and I'm going to put the squared on the outside like that for the moment. Can I do something similar for 35? What would it be? 7 times 5. Okay, is everybody good so far? All right. So what we really have is on top 7 times 6 times 7 times 6, right? Because that's what squared means, multiplied by themselves. And on bottom we have 7 times 5 times 7 times 5. Now when it's written out as a series of multiplication steps, we do have the ability to reduce by dividing them. Is what we're really doing. We're not really canceling. We use that word sort of flippantly. We use it for lots of things, but we're really dividing them. But we really have the ability to divide out common factors. So what factors do you see are in common? The 7 on the top and bottom, and then there's another 7 on top and bottom, aren't there? So we are able to reduce those there. How about the 6 on top with the 5 on bottom? Is there any way for those to reduce? There's not. So at this point, all I would do is I would actually multiply back the numerator together and multiply back the denominator together. So 6 times 6 would be 36, and then 5 times 5 would be 25. Now, let me just say it real quick because we'll encounter it a little bit later anyway. I realize that this is top heavy. I get that, and it doesn't really matter. If there is a place for you to need to change something into a mixed number, we'll get to it eventually. The problem will either clearly say so, or it will be natural to do so. So when we get there, I'll make mention of it again. So just because something's top heavy is not a problem. It's totally fine for the numerator to be bigger than the denominator, or for the fraction to be improper, okay? All right. Determining whether fractions are either equal to one another or bigger or smaller than one another. So one of the theorems in your books, Theorem 6.2, says is equality of fractions. It says that two fractions a over b and c over d are equal if and only if AD equals BC. And what you probably remember is something called cross multiplication, right? So you're creating, I had students call that a butterfly before, creating a butterfly around the diagonals. So we'll just do a real quick one because we've already encountered it. Let's say that I had that 3/4 is equal to 6/8. Like we know that's true for other reasons, but if I were to multiply this diagonal, I'd get 24. And if I were to multiply this diagonal, wow, that was the wrong button. Let's try again. This diagonal, I would also get 24. Okay? So that is a property of equal fractions. Now, there's lots of ways to determine if fractions are equal. This is one of them. It's a really nice one sometimes. because like 3 times 8 and 6 times 4, those are multiplication facts that you should probably have memorized, right? They're small enough. That's not too bad. We'll do it on this one, but aside from using a calculator, I definitely do not have a multiplication fact in my mind of what is 144 times 3. I don't. You probably don't either. So while I could do this problem, and I can use a calculator to do it, it may not be the most natural choice. So what I would like to show you on this problem is 4 different ways to do the problem, not because I necessarily care that you know 4 different ways, but because I think that it's always good to know multiple ways to do something so that when you try something with a kid and they just have this glossed over look on their face, you have another option to try with that kid to help them to understand something that does make sense in their world. Okay? So I'm going to show you 4 different ways, and there's others besides these 4. The first one we're going to do is the one that we just saw. It's actually theorem 6.2. So we're going to take that that 3. Actually, let me just make a comment real quick. Notice they're both negative, right? 3 over 12, 36 over 144, they're both negative. So we could rather, if you wish, to just ignore the negatives and just proceed with the 3 over 12 and the 36 over 144. Y'all good with that? Okay, so we have 3 over 12, and we're sort of questioning, are they equal, right? Or determine if they are, and I've got 36 over 144. So if you do have a calculator with you, I would encourage you to go ahead and grab it out. It'll make our process a little faster for this one. And we're going to multiply our diagonals together. I think every calculator that I have touched has been just about out of batteries for the past 3 days. So that one's not going to work. All right, so we're going to take the 144 times 3. What value is that? 432. And then we're going to do the other diagonal. We're going to do 36 times 12. What do we get? 432. Of course, those are equal, so the fractions themselves are equal. It works. If you were doing this in the 5th grade classroom or something like that, you wouldn't do it this way, though, because at least you probably wouldn't, because they're still not using calculators at that point. And it wouldn't be very profitable time-wise to spend a lot of time multiplying these 2-digit numbers or a 3-digit time one-digit number together. But this is one option. All right, let's try a second option. A second option I'm going to talk about is finding a simplified version. So I'm going to write simplify and compare. More of a descriptive phrase than it is an actual process. But I have 3 over 12, and I have 36 over 144. So 3 over 12. What do they both divide by? 3. And if I do that, I get 1 over 4, and that's simplified, right? Yeah. How about 36 over 144? What would they both divide by? Anything they both divide by is fine. What? They do both divide by 36, but did you really know that before you just played with your calculator to find it? Somebody try something smaller for me. 12. You might notice the 12s, because 12's tables are something that kids typically memorize, so knowing that they both divide by 12 would be a common thing. 36 divided by 12 would be 3, and 144 divided by 12 would be 12. I already know the 3 over 12 because it matches that one. If it didn't match, I could continue, right, till completely reduced form, and I would also still get that same 1/4 that I got a moment ago. So if they simplify to the same fraction, they're also equal to each other, of course. A third option is that we could find and I'm just going to write common denominator for a moment, and just in case you're concerned, the last one's going to be finding a least common denominator. Now sometimes when we find common denominators, that common denominator is the least common denominator. That happens sometimes, but it doesn't have to. For example, on this one, if I had 3 over 12 and I have 36 over 144, one way to find a common denominator is to simply multiply the two denominators by one another. So I could multiply this one by 144 and I can multiply this one by 12. Like that's an option. The numbers are very large when I do that. They're not very pretty, but it is an option. And if you're dealing with a little bit smaller numbers, it might be a better or more desirable option too. So what is 3 times 144? I think we did that earlier, didn't we? 432. And what is 12 times 144? 1728. Is that good so far? Now, the denominator, of course, we know matches the 1728 because it's still 144 times 12. What is 36 times 12, just for good measure? Yeah, 432, just like the other one. So once I got this common denominator, these are equal. Now, a least common denominator, and it may not even necessarily have to be the absolute least, but a smaller common denominator than just any arbitrary multiply the two things by themselves, means that you compare the two denominators you already have, right? So if I look at 144 and I look at 12, I should recognize that 12 times 12 is 144. I should, which means that if I multiplied this one by 12, the denominators would match automatically. So I would get that same 36 over 144 by thinking about it as what do I have in common quicker than 1728? And 144 would work. I think 2, 3, and 4 all have some sort of intuitive idea that we can change the fractions to make them the same. I think it's a little bit more mysterious what's going on in number 1. It's a little harder to justify why in the world does that work. It does. It's true. It's correct. But you're much more likely to have a kid say, okay, but why? Sometimes that's a really tough question to answer when kids ask us that. Well, why does that work? You're supposed to say just because I said so. You know you're not. That's not at all a good idea. But we do it a lot, right? Because we don't really know why it works. So these other options definitely would be more satisfying to a child who wants to know the why behind them. Not only are you able to use the theorem 6.2 to multiply across the diagonals and find that things are equal, you can actually use that same idea to find out when fractions are bigger or smaller than one another. So for example, if you had the fraction a over b and c over d, and the first fraction a over b is bigger than c over d, that will only happen if when you multiply by the diagonal, the top down, this one right here, is actually larger. Notice it comes first. So the pattern, like the order of doing the multiplication matters here so that you get your signs right. AD being greater than the BC. And the same is true for less than. It's a similar argument. Using some of these ideas, we can also put values or fractional values in order. Now, if we're simply comparing two fractions, it's simple enough to use theorem 6.3. We can cross multiply, we can be done. The problem is that if you're comparing 3 fractions, there's not a real good way to do that except 2 at a time, which would mean I'd have to take 2 fractions and figure out which one's bigger than which one, and then I'd have to take the third fraction with one of the first 2, and then the third fraction with the other one. And so that's actually a fairly tedious process. Sometimes it's far easier to do an example like when we found the common denominators over here or least common denominators to make those decisions, especially depending on the fractions that we're given. So we're going to take a look at this one because there are 3 of them, and we're not going to use theorem 6.3 because it actually isn't very helpful for having 3 fractions. But what we can do is to recognize that those denominators are all quite similar. I have a 20 and I have a 5 and I have a 10. And so making all the denominators the same is a desirable way to do this particular problem. So if I were to take 13 over 20, it's kind of already in a good form. I don't need to really do a whole lot with it, so I'm not going to. But if I take 3 over 5, what could I do to 3 over 5 to give it the same denominator as the 13 over 20? Yeah, I can multiply its numerator and denominator by 4. And if I do that, I get 12 over 20. So I know that's actually smaller than the first fraction. I've got a relationship between the two. I can do the same sort of thing to 7 over 10. What would I need to multiply the numerator and the denominator here by? 2. So I would end up getting, oops, let me write it underneath so it's the same. 14 over 20. Okay, so which one's the smallest? Yeah, the 3/5, right? So as I'm writing these in ascending means smallest to biggest, ascending order, the 3/5 would be first. You can put a comma if you'd like. I'm going to go ahead and use my less than symbols to indicate the relationship. What's the next biggest fraction? 13 over 20. And then my largest one would actually be 7 over 10. And you guys did such a nice job of actually using the values you were originally given, not the values you adjusted them to give your answer in, which is a good thing to do too. Now, on this one, you might actually not choose to get common denominators. Maybe you will, but you could do something like Theorem 6.3 where you cross multiply on this one if you wish. So let's actually do cross multiplication on this because it's kind of tempting just because there's only two fractions. And then we'll take a look at the other options that we could have done if we'd chosen that. So we'll do option Theorem 6.3 first. And we will multiply along the diagonals. So if I have 21 times 215, what will I get? Let me put equals here. I want to be equals below. Does anybody get a number? 4515. Good. And then the other diagonal would be the 430 times 51.
That's 21,930.
You're right. So very clearly the second 21,000 number is much larger than the first 4,000 number, which means that the correct relationship here is that 21 over 430 is less than 51 over 215. That's one way to do the problem. It's not too bad, right? I mean, if you've got a calculator with you, you don't have to do the big multiplication, but it's not too bad. So that would be one option. Another option would be to reduce the fractions, right? We've looked at that before. So we have 21 over 430. And we had, what was the other one? 51 over 215. I'll put slash common denominator. This one's actually fairly easy. It's not really reducing, but it could be a reducing depending on your numbers you're using. This one's pretty clean to see that the denominator, one of the denominators can become the other one nicely. 215 is half of 430. So if you actually take the second one and multiply by 2 over 2, you would get 102 over 430. And clearly 102 is a larger numerator than the 21 is, so the second fraction's larger. Yeah, well, I'll write it this way for now. We can see it better that way. And because of the lack of specificity in the directions, you actually have one other option here that we haven't discussed. And that option would be to estimate or to reason it out. A lot of times exact answers are really not that important. As long as you get an estimate, you're pretty good. It's actually a true statement. And so if we can estimate this one and we aren't told that that's not a possibility, right, that's not an option, then it might be preferable because it'd be quicker. So if you take a look at that first fraction, the numerator is smaller, and a smaller numerator should be a smaller fraction, right? Sure, like think about like 1/4 and 2/4. With smaller numerator is a smaller fraction. Not only that, but a bigger denominator, which means you're dividing something into more pieces, also makes things smaller. So on this one, not only does the numerator force the fraction to be smaller, the denominator also forces the fraction to be smaller. So it's definitely a smaller fraction to begin with. So that's what I mean by estimating or reasoning it out, is that the second, I'll say first because that's how I actually talked through it with you. The first fraction the numerator is smaller and the denominator is bigger. Both result in a smaller first fraction. So again, our answer would be that 21 over 430 is in fact less than 51 over 215. You could also look at the 51 over 215 and say it's about 1/4. Right? It's kind of like having 50 on top and 200 on bottom. Well, 50 is about 1/4 of 200, right? So it's about 1/4. There's no way that 20 over 430 is about 1/4. It's a way smaller fraction. So that's another thought process on estimation here that could be used. One of the interesting things that happens with rational numbers that does not happen with integers, whole numbers, all the numbers we've dealt with before this, is something called the denseness property. It says the following: given any two different rational numbers, a over b and c over d, there is another rational number between these two numbers. So it's kind of like the idea that I can always split the difference and I can always cut in half, right? So if you're here and I'm here, we can always meet in the middle. Like the song, right? You know what I'm talking about. I know you do. My kids sing it, so you got to know it. Okay. So, yeah, there's a way to always be in the middle. And that doesn't happen with integers or whole numbers, right? Between 1 and 2, there's no other integer or whole number between 1 and 2. There's a number, but it's not an integer or a whole number. But you can do that always with fractions. There's always a number that's in the middle between them. And there's a couple of different ways to find that. One way to find that, it's not this one, but one way to find that, the one that I've already described, is this idea of averaging something together, right? The halfway point. And the way that we do that, sort of like think about what you do with grades, is you add the two numbers together and you divide by 2, right? That finds the midway point, the midpoint or the halfway point. Another way that's really nice with fractions is this one, Theorem 6.5. So if you have a over b and you have c over d, you can actually add the two numerators together and add the two denominators together, and you will get a number halfway in between the two values you started with. It's a very cool fact, and the reason that it matters is because it's actually a whole lot easier to do that than to add two fractions together and divide the fraction that you get as a result by 2. Right? I mean, really, do you want to add 3 over 4 and 5 over 6 together and then divide by 2? Probably not. But adding the numerators together, adding the denominators together is very quick. So here's an example of one where we would really not want to add these numbers together, literally add these numbers together and divide by 2. It would be awful. But if we add them together with the Theorem 6.5, it's not awful. I have 33 and I have 7, and then I have 427 and I have 92, and it's just whole number addition. So what is 33 plus 7? 40. And what is 427 plus 92? 519. That doesn't reduce any. Pretty much the numerator is being even, and having no other factors that aren't even means the denominator being odd doesn't simplify any. This number will be between. And if you aren't sure, you want to convince yourself by way of your calculator, you're welcome to get decimal approximations to think about them. Now, we're not talking about decimals in a formal sense. We'll do that in Chapter 7. But I know you've worked with decimals. It's not like this is a mysterious idea. You know what they are. So if you to take 33 over 427, hit enter in your calculator, it'll give you a decimal. Take 7 over 92 and give you a decimal. And you can actually look at the fraction 540 over 519 turned into a decimal will be between the other two. And you can confirm it. Now, why must there be a number between these fractions? Well, it's back to that denseness property. It's because the rational numbers are dense. That doesn't mean stupid. It's not an insult. That is, you can always find a point halfway. That's how I reasoned it out with you. But it's really true anywhere. So, or part way. Between two numbers. All right. So this would be an example of a type C question from your book, where a student does something and you have to sort of argue or think through the validity of their description or what they did or whether it was a valid thing to do. A student simplified the fraction m plus n over p plus n to m over p. First, what did the student do? You bet. That is exactly what they did. They canceled the ends. In reality, they didn't really just cancel the ends. They actually canceled the plus ends, didn't they? That's what they really did. Why might they believe this is a valid operation? What's leading them to try this on the problem?
The plus 9 is the same on top and bottom.
So they're thinking of it like division would be for like multiplication, right, Emma? So they're treating it like they would multiplication because it works. Let's say it that way. It works with multiplication. In fact, that's been kind of the crux of our whole lesson on this one, right? If I have m times n over p times n, then I really am able to cancel those out and I get m over p. That's what they're thinking about. It's kind of like the idea of, I would really like to think that I could just cancel out the squares, right? But I can't. It doesn't work. And the same is true for the ends at the end. Now, how would you help the student? I mean, obviously you need to let them know that that doesn't work. But how are you going to sort of verify or prove or argue to them why it doesn't work? Because just arguing that it works for multiplication and it doesn't work for addition is probably not going to work for you. You need something more. Yeah, evaluation of numbers is a really good idea. And the reality is most numbers won't work. So you can kind of get away with arbitrarily choosing the numbers and seeing if they work, and they probably won't, and you'll be good to go. So a numerical example is a good way to do that. So let's say, for instance, this is just arbitrary numbers myself, but let's say we have 2 plus 3 over 5 plus 3. What you have to make sure is that you have the same plus 3 at the end or the same plus 2 at the end or whatever. That part's the part that has to match. The other numbers can be whatever you'd like. So if I were to simply add these together the way that they're intended to be done, I would have 5 over 8, right? That's what I'd have. If I were to try to do this process that they're suggesting and cancel it out, I'd get 2 over 5. Now tell me, are these fractions the same? Why or why not? Okay, So I'm getting shaking heads no. You're right, they're not the same. How could you prove or argue to the student that they're not the same? There's lots of right answers here.
I would just go with what they have different denominators.
Okay, but like 1/4 and, or 2/4 and 1/2 have different denominators. So go a little further. And what? And numerators. So I think that you could say something like they're in simplified form and they don't have the same denominator. So if you go with that, I think you could do that. Sure. How else could you do it?
Show the student how to get the same denominator.
You could. You could get the same denominator and compare the numerators. Could you also draw a picture? This one's small enough you probably could. I mean, 5/8, if I drew, a pizza, split it into 8 pieces and drew 5 of them in, I'd have more than half a pizza. And if I drew 5 pieces and I shaded in 2 of them, I'd have less than half a pizza. This is a really nice one actually to be able to argue it from a picture point of view. Not all fractions are nice to do that with, but this one would work that way. So there are definitely different options that you would have for arguing this. So I'm going to jot down that second one that I have just because it wasn't one that you guys had originally thought of. So just to remind yourself that this is actually bigger than 1/2 and this one is less than 1/2. Right? They are. So that's one thought about doing it. Common denominators is great. You could cross multiply, show that the diagonals don't multiply the same value. That'd be another option. So you have lots of ways to justify why these two fractions are not the same. And if they're not the same, then what the error is the canceling out the +3s. That does not result in an equal fraction. Okay, so here's what we're going to do. I have one more example. This seems to happen every semester, this one last example, and the group work doesn't happen on day 2. We'll get to it on day 3. I'm not worried about it. So we'll do this last example next time. But what I'd like to do before we leave is to put you into some kind of groups, pairs or triples or something like that, so that you know who that you're working with. What will happen when we come to class next time is you don't need to have this homework completed, so you're welcome. It means you'll have it to do over the weekend. I'm sorry. But we will do, and we will finish this problem, example 9. We will start section 6.2, and we'll stop with probably about 15 minutes will be my goal, to stop about 15 minutes to the end of class for you to do the group work from section 6.1, the homework from 6.1, then we'll be assigned. Sound good? Excellent.